Hello everyone, welcome back to 3 Deviations. So at this point, I would imagine that most of you are getting a little bit tired of differential equations, integrals, and derivatives. So in calculus so far, we've been dealing with differential calculus, their applications, integral calculus, their applications and techniques, and then some more applications. And then also we've been dealing with differential equations most recently, and those were kind of one of the first applications of calculus. Now the second application of calculus that we're going to look to is its application in sequences and series. So the study of Unit 9 is going to be infinite sequences and series. So we have infinite sequences and series. Now, this is an interesting unit. This is probably the hardest unit in single variable calculus. So we're really dealing with a lot of abstract things. And if you're in AB calculus, you're done. You don't have any more calculus to cover. But if you're in BC or you're in calculus 2 or single variable, you still do need to cover this. So we're going to cover infinite sequences and series. This is a topic that deals with sums or lists of numbers, at least at the start. We're looking at lists of numbers and sums as they go to infinity. We're going to see what they converge to. And then we're also going to apply this to approximating functions. So that's something you maybe heard in physics called like a Taylor approximation. We're going to be looking at that later in the unit. But anyways, this is probably going to be our longest unit, and it's probably also going to be our most challenging. So we're going to start together with sequences. This should be a nice break. This should be stuff that you recognize from calculus, and then we're going to bring some limits in a little bit later on in the video. All right, let's get started. So as you should know from pre-calculus, we have the definition of a sequence is simply a list of numbers. And so that's like I could have oh, that was a bad curly bracket. I could have 1, 2, 3, and then we could keep going. That is all of the natural numbers. So for that we write an n. Or I could have I could add 0, then we could do 1, 2, and then we could keep going. That is all of the whole numbers. But you know, these are pretty elementary. These are just sets of numbers. We can also have sequences that are just finite lists of numbers, and that is kind of what you deal with in pre-calculus. But now we're going to start dealing with sequences when we keep going out to infinity. So like all of these numbers, all of those numbers. And when we are just dealing with integers, things can get pretty boring. We know that those are all going to go to infinity. If you keep adding all the numbers, they go to infinity. But once you bring in the fractions, then that makes it a lot more interesting. So anyways, we can have arithmetic and geometric sequences. So if I have an arithmetic sequence, that means that I am going to have some sort of starting number, and then I'm also going to have a common difference. So these two numbers define a sequence. So let's say that a sub 1 was 1. So a sub 1 equals 1, and the common difference equals 2. Well, if I do that, then my sequence is going to be all of the odd numbers. So I'm going to have 1, 3, 5. We're going to keep on going, right? Then we can also have a geometric sequence. So geometric sequence is once again defined by its first term. We'll use 1 again. And it's also defined by a ratio, which is we'll call 2. But anyways, a common difference, you keep adding the common difference. But with a geometric sequence, you keep multiplying by the common ratio. So I could have, if 1 is my starting term, I'm going to multiply 1 by, so I'm going to have 1, then I'm going to do 1 times 2, then I'm going to do 2 times 2, then I'm going to do, a second. Yep. Well, we keep defining these numbers all based on how we are writing them. So the formula for an arithmetic sequence, a sub n, is equal to a sub 1 plus n minus 1 times our common difference. And then for a geometric, it is defined as a sub n equals a sub 1 times the common ratio to the n minus 1th power. So you can kind of see a little bit of a similarity there, right? So These are two elementary sequences that we know very well from pre-calculus, but we are going to spice it up a little bit later in the video. Let's just do a quick example with something that we should also be familiar with, which is finding expressions for sequences. So we're going to use a little bit more challenging of an example here, but we should be able to do it. So let's find the nth term of the following sequence. So we've got 3/4, then we got -4/16, then we've got 5/64, then we've got -6/256, and we can assume that this keeps going on forever. It doesn't need to be just 4 terms. Anyways, I could have written this a little bit more subtly as 1/4, and then you would have needed to fiddle around with it, but I think we're good. So let's try to solve this. So what do we see? Well, we see that, first of all, this is alternating. So we're jumping from a positive term to a negative term to a positive term to a negative term. So we keep jumping between signs. So that means that our sequence is alternating. This is something that's going to be so important to recognize. So we've got an alternating sequence. So that means that we're going to need some -1 to the nth power, -1 to the n-1th power if we're starting at 1. So that is how an alternating sequence works. If you have this -1, well, if you raise -1 to a negative power, you get a negative number. But if you raise it to if you raise it to an odd power, you get a negative number. But if you raise it to an even power, then you get a positive number. So we can kind of see this alternating sequence. We're starting with a positive number. And then we can also see that for the first term, we've got 3, then 4, then 5, then 6. Well, we're just adding 2 to whatever the term is. So we know for the numerator, we are going to get n plus 2. Now the denominator, this is something that I think that you should all find very easily. These are all of your powers of 4. So you've got 4, 16, 64, 256. It's raising 4 to the nth power. So you've got 4 to the nth power there. Then we've also got this little alternating series bit, so we've got to add this -1 to the n-1th power, right? And that's exactly what we're looking at here. So that's an example of finding a sequence. This should become second nature to you once we keep going through them. So that is how these sequences work. All right, now let's talk very briefly about limits. I don't want to spend too much time on this because sequences is really the secondary thing that we're dealing with. We really want to focus mostly on series, though that's what's really important. Limits of sequences, it's very similar to limits of functions. So if the limit of a sequence is some value L, then the sequence converges, and if it's infinity, then it diverges, right? So if I have the limit, and this should make sense, right? So limit, if I have limit as n approaches infinity of a sub n, and that's some value, well, that means that if I plot this out, what's going to happen is I'm going to have, maybe I'll have a term here, I'll have a term there, 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 I'll have a term there. We keep on going like that. Well, we are converging to some sort of value. All of our terms are asymptoting at some point, and this would be that value L. However, sometimes when we take the limit as n approaches infinity of a sub n equals infinity, well, then that means that we are having terms and they're just ballooning up. So like proportional, like n squared or something, or e to the n, then we're obviously gonna get way too big for a sequence to converge. So that means that it diverges. So this should be pretty easy. If you can, we talked, I think, in one of our first videos about taking limits at infinity. So if you can take limits at infinity, you can find the limit of a sequence. You can determine if it converges or diverges, right? That should be fairly easy. All right, in the next video, we want to talk about series. So we're going to introduce series. We're going to talk about telescoping series. We're going to talk about the harmonic series. And then we're going to talk about what happens when those guys go to infinity. So after that, we're going to talk about really what strategies we have. Similar to integration techniques, we have techniques for checking if a series converges or not. If so, what does it converge to? So we're going to be spending the bulk of the unit talking about that. All right, we'll see you then. Bye.